In this screencast, we'll talk about coding programs with Gődel numbers. So suppose that we have a program, and the formalism that we have been using is the programming language L, which is developed in the book Computability, Complexity, and Languages by Davis, Waker, and Segal. We're gonna, although it can be any formalism, the technique that we will discuss in this screencast can be extended to any formalism, any programming language, although with significant modifications. So we're gonna take the program, feed it into the Gődel coder, and the Gődel coder will compute a natural number. In other words, the program P will be mapped to the number of P, which is a natural number. And then, so that's the compilation. And then later on, we'll talk about the process of reverse compilation, whereby we take the number of the program, some program, and then basically extract the source code. So in theory of computability, instead of compilation and reverse compilation, we'll be using the terms coding and decoding. So coding means that, well, you take a statement in some formalism and you map it to a natural number, and then decoding, you take the natural number and extract from it the statement that is encoded by that number. So we'll do it in 3 steps. The first step is we're going to figure out how to code variables and labels with numbers, right? Well, Gődel numbers. Right? Then the second step is how to code instructions with numbers. And if you may want to refresh your memory on the syntax of L, by watching a couple of previous screencasts on this channel. And then once we know how to code variables and labels, well, we'll figure out how to code entire programs, because programs are nothing but sequences of instructions. Okay, so just to review, so the labels that we have in the programming language L are A1, B1, C1, D1, E1, and then A2, B2, C2, D2, E2, and then A3, B3, C3, D3, E3, and so forth. So we can arrange them in this list, right? And the list is infinite, obviously. So labels can be arranged. We assume that they are arranged in this list, and the list can obviously be effectively computed. We can write a procedure that enumerates all of the each and every label, right? So label number 5, label number 15, and so forth. And we can arrange variables in a similar list. Y is going to be the output, and it's going to be the first variable in that list, and x1, z1, x2, z2, just to remind you that x's are input variables. We can think of it as registers, and then z's are internal variables. So y, x1, z1, x2, z2, x3, z3, x4, z4, and so forth. So if v is a variable, then the number of v will be defined as the number of the variable in the in the list of variables, or the position of v in the list of variables. So, for example, the position of a1 in the list of y in the list of variables is 1, and then the position of x 1 in the list of variables is 2, and so forth, right? And then if L is the label, then the number of L, right, hash and then parentheses L, the number of L, is the position of that label L in the list of labels. Labels, right? Okay, so here's a couple of examples. So the number of the position of y is 1, the position of x1 is 2, the position of x3 is 1, 2, 3, 1, 2, 3, 4, 5, 6. Then the position of, let's see, let's have another example. The position of Z2. Okay, 1, 2, 3, 4, 5. Okay, and then the similar technique can be applied with labels. So the position of B1 is 2, right? A1, B1. Then the position of A2 is 1, 2, 3, 4, 5, 6. All right, and so forth. Well, and obviously it is primitive recursive, but both of those functions can be computed in a primitive recursive fashion. So the label position, the position of the variable, and the position of the label. Okay, so the next step is we're going to be coding the instruction types. So we have 4 instructions in L. The first instruction is sort of this self-assignment, right? V goes to V. And this we will think of this as the instruction type 0, right? Then the second instruction type is V is assigned the value of V plus 1, the increment, and this instruction, the type of this instruction will be 1. Okay, the next instruction is the decrement. V is assigned the value of V minus 1. And the position, okay, the instruction type in this case will be given the value of 2. And these values are, well, arbitrarily to some extent. So it's just a convention, so other values may work out so long as we can guarantee the uniqueness of a number, the produced number. Eventually, we have to code every instruction into a unique number. And then the fourth type is the dispatch, the conditional, right? If the value of V is not equal to 0, then go to L, to some label, and the instruction type is the number of the label plus 2. So just to make sure, plus 2 will become clearer later on, but we just don't want the instruction type to be of 0. That's why we're writing 2. So it guarantees that it's not going to be 0. So if I is a primitive instruction means that it's not a macro. So we have discussed L macros before, but each macro can be decomposed into a sequence of primitive instructions. So it's not a loss of generality. The number of the instruction can be encoded as the pair, right? So we talked about the pairing function. So it's the pair of A and the pair of B and C, and A is the label number. If the instruction has a label, then A will be encoding the position of the label in the list of labels that we talked about just a couple of minutes ago. B is the instruction type, as discussed again on in just a few moments ago. And then C is the number of the variable used, though the position in the variable list used in the instruction. So it's this number of V. Okay. So that's that. So if I, which is a primitive instruction, is unlabeled, then obviously A will be 0. And if I does have a label, right? So to the left of it, it's a labeled instruction, then A will be equal to the number of the label used in that instruction, or the position of the label in the variable list, right? I'm using those terms interchangeably. And if the variable is which is used in I, v is a variable which is used in I, then C will be equal to the position of the variable in the variable list minus 1. Well, that means that why minus 1? So that if the variable is y, C is equal to 0, because the position of y is the first in the list, so 1 minus 1 gives us 0. If I is the self-assignment or no op, then B will be equal to 0, right? So that's the type of the instruction. If I is of the type V equals V plus 1, so the increment, then B will be equal to 1. And this is just a convention, right? And if I is of the type V equals to V minus 1, V arrow V minus 1, then B is equal to 2. Okay, and finally, if V is a dispatch, a conditional dispatch, so it's of the type if V is not equal to 0, then go to L, where L is some label, then B will be equal to the position of L, the position of L, minus 2. I'm sorry, plus 2. Plus 2. So, and why plus 2? Because B for the conditional will always be strictly greater than 2. Because the position of L is 1, at least 1. So, it is strictly greater than 2. So, we will not confuse the conditional with the other instruction types. So let's go through an example. Let's suppose that we have I, which is of the form x equals to x plus 1. No, when the subscript of 1 can be omitted. So that's a convention that Davis, Wayaker, and Segal used in their text. So what's the number of this instruction? Okay, so remember that it's the pair of A and the pair of B and C. Right? A is equal to 0 in this case because we have no label. It's an unlabeled instruction, so there's nothing to the left of the left x. And now, because I answer, oh, so what's the value of B? B is 1. Why? Because the instruction is of type plus, right? So it's the increment. So addition. And finally, so C will be the number of the variable, position of the variable used in the instruction, which is x, x1, because 1 is omitted, minus 1. So, and the position of x is 2, so 2 minus 1 is equal to 1. So, that instruction is encoded or mapped into the integer, which is the pair of 0 and the pair of 1, 1. So, let's work it out. It's 2 to the 0 times 2, and then times the value of this pair. Plus 1 and then dot minus 1. This is the formula. Okay, so this is 2 to the 0, and then 2, let me use the square brackets to compute the value of the pair 1, 1. So it's 2 to the first, 2 times 1, plus 1, and then dot minus 1. So that's the value of the pair of 1, 1 plus 1, and then dot minus 1 dot minus 1. So okay, this is equal to 1 times 2 times this is equal to 2 times 3 dot minus 1 plus 1 dot minus 1. Okay, this is equal to 11 dot minus 1. That's equal to 10. Okay, then let's add the label to the previous instruction and compute its number. So the value of the label is A1. So that's a labeled instruction. So what is the number of this instruction I? Okay. All right. So again, the number of I is going to be the number of the label, the position of the label in a list of labels. Then 1, because the instructions of type addition, and the number of x1. Right, and x1 is the same as x minus 1. Right, so the position of x1 in the list of variables minus 1. So this is 1 and 1 1. Okay, so and that is going to be 2 to the first times 2 to times 1 1 plus 1 dot minus 1, and that should be equal to 21.